So it's first time. This is a Google Meet. I see. Where do I share my screen?
Okay, it is something in present now.
Present
below
now. Okay.
That. Yeah. Subudhi sir, do you have the biodata of Professor?
Yeah, I have.
Okay, sir. Thank you. তুমি অলপ ফোন কৰা না বিকে ৰয় স্যার প্লিজ।
So good afternoon, Professor Roy.
Yeah, sir, welcome. BK Roy, sir.
Yeah.
Good afternoon, Professor Roy.
Very good afternoon.
Good.
So, how is life in Goa now?
Goa is always Goa only.
Goa is always Goa only, huh?
Yeah.
It's a mood.
So, Professor Roy, let me introduce you to Professor Jason Gu. He is here, and
Very good morning, Professor Gu.
Oh, morning, Professor Roy.
Yeah.
So I think we can start with the session, Professor Subudhi. So I at the outset, let me welcome Professor Vidyadhar Subudhi from IIT Goa. He is a renowned researcher in control theory. Had his PhD from Sheffield University, UK. Had his postdoc from Singapore, and he has established himself over the years in robotics and its control strategies. He is well known in India and abroad for his research credentials, and has produced so many PhDs related to robotics. And I think he is someone who is well known in underwater vehicle robotics too. So I also welcome Professor BK Roy to this session, who is also a researcher of control theory and applications from NIT Silchar, and who is known now in our country and abroad on nonlinear control, nonlinear dynamics, and chaos. So welcome, Professor Subudhi, Professor BK Roy. Welcome, Professor Jason Gu. You will be introduced to the session by Professor Subudhi. I also welcome the session co-chairs. I think I myself is a co-chair. I don't know who is. By the way, the things are so getting confused to me. Yes, I am the co-chair. So I welcome all the participants in the Google Meet, as well as the participants who are viewing us live on YouTube. So over to you, Professor Subudhi, to start the session.
A very good afternoon to all in this cloud environment for this session, plenary session. And I take this opportunity to thank Dr. Rajiv, who is very much dynamic in the professional activities over the couple of years I am seeing. And I think Professor Roy and Professor Rajiv, they're making a very interesting group to take off many new adventures. And we are really meeting a very wonderful plenary speaker today. I am privileged to introduce Professor Jason Gu to all my colleagues in this cloud environment to this plenary session. Professor Gu is a professor of robotics and assistive technology in the Department of Electrical and Computer Engineering at Dalhousie University. Professor Gu's research areas include biomedical engineering, biosignal processing, rehabilitation engineering, neural networks, robotics, mechatronics, and control. Professor Gu has published over 300 plus publications in prestigious journals, book chapters, and conference proceedings. Professor Gu is a IEEE member of SMC and Robotic Automation Society, and has been the editor for the Journal of Control and Intelligent Systems, transaction on CSME, IEEE transaction on mechatronics, IEEE transaction on IEEE SMC magazine, International Journal of Robotics and Automation, and IEEE Access. Professor Gu is a Fellow of Engineering Institute of Canada and Fellow of Canada Academy of Engineering. He is currently IEEE Canada President for 2020 and 2021. So we are really fortunate to have him here today for this plenary session, and he will be delivering his plenary talk on teleoperation related research activities at the Robotics Lab for Biomedical Rehabilitation and Assistive Technology today. With this short introduction, I once again welcome Professor Jason Gu to this plenary session, and I request him to take the session for further proceedings. Thank you very much.
Thank you. Let me just share my screen. Just a second. Can you see the screen?
Yeah, we can see. Yes,
Yeah.
yes.
Okay. Thank you, Professor Saptuhi, for the introduction. And good morning, Dr. Day and Roy and everyone. For me here in Canada, but good afternoon for you guys in NIT Silchar. Thanks to Dr. Day for the invitation to give a plenary speech at the International Virtual Symposium on Control, Communication, and Embedded System for Robotics. So this is Jason Gu, professor at the Dalhousie University in Halifax, Nova Scotia, Canada.
Professor, can you show in the slideshow mode? Slideshow mode, please.
Slide what?
Slideshow, the full slideshow mode. It is, you press the slideshow mode, or you share the entire screen.
On the presentation mode, I mean presentation mode of the slide.
You didn't see my screen?
No, we are seeing, but it is not the full screen slide.
Okay, just
yeah.
Okay, let me see if I can.
F5.
Is that the full screen now?
No.
Let's just a second. Let me see what's the issue here. Let me presenting.
I think you have to share the entire screen. Click
entire screen.
Yeah.
Okay. Entire screen.
Yeah.
Can you see the entire screen now?
Yeah, we can. Yeah.
Is that the full screen now?
Yeah. Perfect.
Yeah, it's perfect.
Thank you.
Okay, good. Thank you. So I will continue. So due to COVID-19, now we cannot visit each other. Actually, I have been home since March. It's been a long time, but we always use the meetings like a Google Meet, Webex, and Microsoft Teams, Zooms, and etc. So we meet in cyberspace. Hopefully, when things getting better, then we can visit each other. So today my talk is about teleoperation related research at Robotics Lab for biomedical rehabilitation assistive technologies. First, just let me briefly introduce my lab. My lab actually is founded by the Dalhousie University and also National Science and Engineering Research Council. We have all kinds of robotics arms, mobile robots, humanoid robots, omni bundles, and many workstations. So we have carry out the research in the mobile robotics, teleoperation, assistive technology, and medical robotics. So here's some research support we have received from National Natural Science and Engineering Research Council and Intercollaborative Collaborative Research Development Grants. And Nova Scotia, it's our province. We have Research and Innovation Trust, and we also have Canadian Foundation for Innovation. Nova Scotia, we also have the National Research Council. We have industrial research assistance programs. And also there's a hospital here. It's Queen Elizabeth II Hospital. And also there's International Science Technology Partnership. So there's some list of projects that we did in our research lab. I'll probably just very quickly go over that. This page showing some project we did from 2000 to 2004, on the sensor fusions in the mobile robotics, and also sensor fusion for robotic eye project. And also we have received the infrastructure fund from a Canadian Foundation for Innovation to set up the labs. This page showing the fund from 2004 to 2009, talk about the product. That's the one I mentioned also in the medical telesurgical robotic applications and the climbing robot, and also we have project talking about using the robotic hand, for help and physical challenge the person. There's some fun here on the mobile robotics, and also we also develop user control technology to develop the linear generator system for ocean tidal and wave energy. This is the collaborative project between Canada and China international project. And also we have integrated training program in 2008-2014 for biomedical devices and innovation. We also have a project to do the sensing and the fusion for mobile robotics. Here's some product in the mobile robotic control with MI magnetic technology, and also we developed the platform for senior and disabled. There's also some product using multi-signal fusion for telemonitoring. Also, there's another project. It's a collaboration between Canada and China for biomimetic robotic eye development. So here's more product. One is we work with Industry Auto 21 to develop an electromagnetic suspension system to improve the vehicle fuel efficiency. And there's another one in the power system for prediction analysis control. And so we always continuously receive the fund from that's the National Science Engineering Research Council called Discovery Grant. So every 5 years you have to apply, and then you're being funded to continue a project. So this one is on the sensing control multiple mobile manipulator. There's also industrial fund that we can use to support the both PhD and postdoc fellows. So it's called a MyTax. So we use that to develop different kind of algorithms, particularly when you have a highly related industrial applications. So working with the industry. This one we will explain just the product we're working with Dr. Day initiated by India government. So here's the one, the project we just recently received. So total fund I just mentioned over a list of received $4.5 million Canadian dollars support from the government and the federal and the provincial. But most recently we received this 1.65 million fund, and plus some also contribution from industry and also from Dalhousie and around the 4 Atlantic universities add up to around $2.2 million Canadian dollars to support project on the interdisciplinary marine engineering research and industrial training. So for this project, it's a team project. I'm the principal investigator. So there's 4 research themes. One is on the autonomous marine system, and another one is acoustic, fiber optical, and in-situ sensing. Third one is the marine electronics and the controls, and the last one is the big data analysis for marine research. So we have a co-applicant there on 4 professors in 4 Atlantic universities. So here we have Dalhousie University, and also we have University of PEI, and there's University of New Brunswick and Memorial University. And also we have around 10 collaborators and industrial partners in this project. There's also industrial collaboration, so supported. We have received funds from ESSO, Imperial Oil, Navy Track, and etc. For the research. Some in-kind of support from companies, Mitsubishi, iRobot, and QE to the hospital. We have so here's some associated, but it's not complete. That's the people that are working in the lab. We can see Dr. Umar and Assad here. So they're all working in the lab, so carry out the research work. So this is the one I particularly want to mention. This is a project I've been collaborating with Dr. Day and at Kikari. So the project, the title is the Investigation Development of a Robust Control Strategy for Nonlinear Bilateral Teleoperation System with Delayed Communication Experimental Validation for Rehabilitation for the Stroke Patient. So this project is a scheme for promotion of academic research collaboration, Government of India initiative. Okay, so before I talk on the teleoperated operation project, try to talk a little bit of research activities in our lab. As you can see, the fund we have listed. So we one part of that work is control of mechatronic systems. There are manipulators, mobile robots, and underwater robotics. So we kind of carry out the research in all kinds of robotics area. So publish papers and in that area. And another one is control switch converters, such as DC-DC, DC-AC, AC-AC, and conversion systems. Third part is, as we already also know, that artificial intelligence has been attracting lots of attentions. We also did some work in that area, use neural fuzzy networks, extreme learning machines, and deep learnings for robotics control. The neural fuzzy networks, I will cover a little bit there. We use that to do brain motion learning network, and also we design our architectures for teleoperation. As for the extreme learning machines, also being used in computer visions. We also have some associates are working in that area, and or same thing for the deep learning. So yeah, AI, one thing is using for the control. There's another big portion is used for image processing and computer vision. I'm not going to cover that today, but yeah, it's been also a very heavily researched area, and lots of algorithms have been developed, and also they already had industrial applications. So, so this is just a brief introduction. Now, in this talk, basically, we will have following content. So we'll give a very brief introduction on teleoperation. and then talk about applications in the areas of teleoperation and existing architectures for the teleoperation. And then we will talk about some architecture we proposed and algorithms we developed for different teleoperations. And then at the end, I will conclude my remarks. So in the presentation, I'm just first taking out some notations. The blue means the basic ones, basic network, basic configurations, and red lines means the communication channel. So in a teleoperation, there's always a tele, right? So there's through the communication channels to sending and receiving the signal. So we use the red one to represent the communication channel, and orange to represent the signal transmission. Green ones color will be used for differentiable features, and the CN one will be used to means what have been improved, some enhancement in the existing architecture. So this is just a very general model of teleoperation. As we see, we have the human operator will be, operator will control the master manipulator. So and then the position, velocity, and forces will be sending through the communication channel remotely to the master, to the slave. Right? And the slave will receive the command and then will interact with the environment. And there will be feedback. So there will be position or velocity or the force feedback. The feedback will be sent back to the master through the communication channel. So this is just a very basic teleoperation model. There's lots of applications for teleoperation, as we can see. I think some showing here, top first two here is showing using the this one probably is the one for the French robot. So they're using the consoles to control remotely the robot to carry out the surgical tasks. So that's called surgical robot. And there's also people can operate the remote either vehicles. So this is a more moving vehicle with manipulators to carry out some tasks, maybe in a dangerous, maybe in a nuclear field or remote places, and even in outer space, to fix the satellite or clean the dust, and doing some maintenance. So that's to do the teleoperation for the aerospace. So there's lots of applications for the teleoperation. When you have the robot to the remotely, then you have to control them to carry out the task properly. And so there's lots of algorithms being developed in this area. So here's the common existing architecture for the teleoperation. There are 2 channels and 4 channels architecture. For the 2 channels, as you can see, the masters were sending either positions, speed, and force to back and forth the slaves. As for the 4 channels, we can have the master sending either the position, the velocity signal, and the force. And similarly, from slave to master, you also can sending out the signal, position, or velocity, and the force. Right? So that's the 4-channel architecture. So here's some research work in the teleoperation at our robotics lab. We have non-passive approaches and the passive approaches. So passive approaches, we did the work on the power-based time domain passivity architecture. And so for more of the work I will explain here is some non-passive approaches we carry out. There's a motion equivalent force architecture and composite state convergence architecture. This being done by my PhD, and now it's a professor for state convergence. And also there's some enhanced architecture, to improve in that. So this is the motion equivalent force architecture. So this is a family of this architecture where equivalent force is transmitted from slave side or master side transfer either full state or only the position information. The terminology of equivalent force refers to the parameter that will allow to reconstruct the remote environment force at the master side, This is a family of the composite state convergent architecture family of 3-channel. So there are 2 scalar variables transmitted from a master. As you can see, one is the combined position velocity, and the one is the operator's force. As for the slave back, is just combine the position and the velocity. So in the enhancement in some existing teleoperation architecture have been made by the architecture modification and all by introducing more capable controllers. So there are disturbance observer based 4-channel architecture. There's a disturbance observer based state convergence architecture. And also we have the fuzzy model based state convergence architecture. So this is a 5-channel architecture. So here both the position and velocity signal are transmitted from the master side, while estimated environmental stiffness, damping, and constant transmitted from the slave side. Disturbance observer is used on the slave side to measure environmental force in the combination with the sliding mode control to track the master system trajectories. On the master side, the estimated environmental parameter estimated are used with the master state information to produce environment force, which is used in the master controller to provide the operator with a sense of remote environment. So they're showing position velocity from master to slave, and here is the environmental stiffness, damping constant. So this is the control law for the slaves derived. The slave one is on the left side, while for the master is on the right. So 1 degree freedom module being assumed here. In the slave model, we have FAXD is theta is the module parameter, and phi is the regressor vector. External force estimated using disturbance observer for using the slave control law. At the same time, the environmental parameters are estimated and transmitted over the communication channel to the master side. So the environmental force is reconstructed with the help of the estimated parameter, and the master control law is updated with this estimated force. So on the left side, we show in the experimental setup, a slave is to interact with the sponge. So we can push the sponge. As you can see, the slave is following the master, and the environmental force is also properly reconstructed by the proposed algorithm at the slave side. The environmental stiffness, damping, and offset terms show as estimated by the proposed technique. So as compared to the previous architecture, we have reduced the number of channels. Previous one is 5-channel. Now this one we reduced that to 4-channel. So allowing only a position signal from the master. So that's the position signal from master to the slave. While 3 estimated parameters from slave side remain the same. The position signal is transmitted from master side. Signal processing block generate. So we add a signal processing block, generate the velocity and accelerate signal through derivative filtering for the slave side. In addition, master and slave device parameters are also estimated to improve the tracking performance. So we have a master parameter estimation and this and slave parameter estimation. So we have both sides. We have those estimators added to improve the tracking performance on both sides. So here is the master and slave as well as external force parameter estimated using the projection type adaptive law. Estimate slave parameter are used in the slave control law, and while master plus environmental estimated parameters are used in the master control law. The environmental force is reconstructed using the transmitted parameter from the slave side. So we're showing some results. We conduct the experimentation on the 2 rotary voice coil motors in the D-space control environment. On the right side, the parameter estimation result of master side show similar to the slave side parameter estimation show, and environmental parameters are well estimated as well. And finally, the position of force tracking results show that the proposed scheme indeed offers transparent teleoperation. So here we introduce the 4-channel motion equivalent force architecture to make it more practical. Master and slave parameters estimators are removed. In the previous one, we have the estimator. So here we remove the master slave parameter estimator, and master plus slave planner are introduced. So we have the master trajectory generator and a slave trajectory generator. So introduced to generate the desired trajectories for the master and slave side. Note that the force sensor is now equivalent at the slave side. However, the position and the force tracking profile improved. So here side is the control algorithm. So we consider a multi-degree of freedom manipulator as a master and a slave devices. Slave control law contains the radial basis neural network terms to approximate the uncertainties. Adaptive law for weights of a neural network is derived through the Lyapunov analysis, and a radial basis network is also used to estimate the environmental force. The weight of a neural network transmitted across the channel, and the environmental force is reconstructed for use in the master control law with the help of a master motion planner. So here's the validation. Experiment studies being carried out using 2-link manipulators. Results show that the proposed schema exhibits the excellent position of force tracking behavior. At t equal to 20, pulse disturbance is injected, and then the proposed scheme is able to maintain stability in the tracking. Superiority of the proposed scheme is also evaluated by comparing its performance with 2 other telecontrollers in circle drawing tasks. As can be seen, the proposed offers the lowest robot root mean square error, RMSE. And this is due to the fact proposed scheme can estimate the uncertainties to an excellent degree of accuracy. This is a family of 3-channel architecture. In this architecture, a combined position and velocity signals are transmitted from a master to the slave side, which make up 2 channels. And the operator force is transmitted on the 3rd channel. So the force is 3rd one, and the slave and master slave to master, master to slave. That's the 2 channels. So this is a 3-channel architecture. So this 1-degree freedom teleoperation is considered here. The control law for the master using user states as well as a function of the states. The closed loop composite master error system is derived with the proposed control law, and error is allowed to evolve as autonomous. The desired closed loop dynamic response is then assigned to the master error composite system. After solving the design conditions, closed form expression of the control gains are derived, as can be seen here. The control gain are dependent on system parameters. So this is the limitations overcome through the disturbance observer, as will be shown shortly. So here's the proposed composite state convergence schema testing. So we use the MATLAB and Simulink and also the Quark environment. Quark is the software provided by a company called Quasar here in Canada. So we bought their devices, and they also have this open architecture so we can use. So then we can do the simulation, and also at the same time we can also do the hardware testing. So the environmental environment where a slave is considered to be a virtual system, while force feedback loop is closed around the operator. And a constant operators of force, all the composite and original state convergence can be seen on the right side. Scheme also presented the force reflection behavior as had been seen in the results. And the varying operators of force, the slave is able to follow the master with a little bit time delay. As you can see, the red one is the slave, and this blue one is the master. So you can see the slave can follow well with the master, with just a little bit delay there. And the purple force is also displayed to the operator. So here's another 3-channel composite state convergence architecture to deal with parameter uncertainties through the use of distance estimator. So you can see there's a distant observer being designed and added in both master controller and the slave controller. So this is a 3-channel architecture. As can be seen, the control law are updated with estimation of the lambda uncertainties as well as estimated velocity, while other design procedure follow the composite state convergence scheme as a brief we did earlier. So here's some study results. During simulations, we consider 1-degree freedom teleoperation by modeling the master and the slave as a double integrated system, while all other terms as a lambda uncertainties. As can be seen, the state of the master and slave system converge under a step human force. Experimental results also show that the state of master and the slave system converge, and the disturbance is actually accurately estimated by the disturbance observer. Comparative analysis with genetic algorithm optimized environmental force compensated PD controller reveals the superiority of the proposed scheme. So here we just showing the tracking through on the left side is the EFC PD controller. This side is a position tracking through the proposed controller. So we do the comparison. As you can see, easily you can see from left side, the slave didn't track well following the master. As our proposed controller, the slaves is tracking very well following the master. In addition to the proposed new architecture, research is also conducted to enhance some of the existing architectures. The 4-channel standard, we all know the 4-channel, it's a very basic standard architecture, is improved by lending master and slave planner from our motion equivalent force architecture, as shown on the previous slide. So you can see there's a master trajectory generator, and a slave trajectory generator. The position of force tracking ability of the standard 4-channel architecture will be improved. So this is the, as you can see, I said this is the enhancement part of the previous 4-channel architecture. So here's the also the we have this planner added, and then the corresponding algorithms also being developed and implemented. So we will just show some results here. So the proposed enhancement in the 4-channel architecture is tested on a multi-degree of freedom teleoperation system. First, the performance of a standard architecture is shown. And now the performance of enhanced architecture is displayed. So it is evident from experimental results that the transparency of the system is improved by virtue of the disturbance observer, which is able to compensate the modeling accuracies and the disturbance. As can be seen here, the disturbance estimate area of the order 10 to the power minus 3 for both the joint of master and the slave manipulators. So you can see the great improvement in this enhanced architecture. Also, enhancement is introduced in the state convergence architecture based on the TSA fuzzy master controller and TSA fuzzy slave controller. So, so we introduced the TSA fuzzy network in the state convergence architecture. Okay, so both the master and the slave controller are now able to ensure a large range operation of teleoperation while sticking to the symbiote elegant design procedures. So it's a kind of a nice combination. You know, for the state convergence, there's a very nice elegant design process. And now when we kind of integrate the TSA fuzzy master and the TSA fuzzy slave, and then when you introduce the fuzzy system there, you can increase the range operator, the range of the operation. So that's the nice feature to integrate these two together. So here we consider the teleoperation system TSA fuzzy space and the design a novel parallel distributed compensation to enable the use of the state convergence scheme. But this showing just all the mask here showing there's a 3n plus 1 conditions then it has to be solved to determine the control gains. Here's some showing the results. The simulation conducted on a single degree of freedom nonlinear teleoperation system. As evident from the simulation results, the proposed enhancement enabled large range operation when compared to its linear counterpart. In achieving this enhancement, the method of state convergence is followed. So this is the existing 5-channel state convergence architecture to deal with systems uncertainties is improved by designing the disturbance observer for the master and slave systems. So you can see we this 5-channel state convergence architecture, we added the disturbance observer for the both master side and also the slave side to improve their performance. So the state space model of the teleoperation system involving uncertainties is considered here. Extended state observer is constructed by consider extended state space model, where the last state is the lambda disturbance. The control law of the state convergence architecture are updated with the estimated state, and the disturbance state is canceled, as we will see with actual terms appearing in the controller. The design of the control gains is based on a state convergence procedure. So we explained that before, so I'm not going to repeat here. To test the enhanced architecture, experiment carried out on a single degree freedom teleoperation system in Maglev, Simulink, and a Quark environment. It can be seen that disturbance observer successfully estimate the uncertainties and the disturbance compensated the master-slave control loss to ensure the convergence of the position and the force errors to neighborhood for origin in a state. New control architectures developed in our lab also being extended to cover the area of multilateral teleoperation. So before, when we introduced that, we all just talk about the one master, one slave, right? So then we can extend that to multilateral teleoperation. So you can have multiple masters and also multiple slaves. You have 2 master, 2 slave, or 2 master, 3 slave, and etc. So more than one master slave device that involved to perform a certain task. Sometimes you just have one is not enough. As I showed in the before in the area, you can see the robot to doing the medical surgery. So you need to, just like a surgeon, you need to have 2 hands together. So then sometimes they have even more. For the finishing, they have like 4 robots working together. So you have 4 master slaves there. Then this side, you also need to have multiple masters. So they're involved to performing certain tasks. You can see that the motion equivalent force architecture, only position signal is transmitted from master side to slave side with environment parameters from slave side. So we extend that to an M-master and slave teleoperation system. In this case, position signal from all masters are transmitted across communication channel, where environmental is acted upon by multiple slaves, and only environmental parameters are transmitted, as was the case for bilateral teleoperation. So this is the extension from just a single master, single slave to multilateral teleoperation. So the dual master, dual slave operation, that's the first one we start, is show that the desired object trajectory is being well tracked, as the error of is very, very small. Similar, the master slave manipulator are also tracking the desired trajectories as determined motion planner blocks. Here, the motion equivalent force architecture with a radial basis function and a neural-based adaptive robust control is extended to operate a multilateral teleoperation system. Again, communication structure contains all the master position and the signal and the environmental parameters. The dual master and dual slave teleoperation experiment has been carried out. As you can see here, here's the setup. The desired master and the slave trajectories, again, being well tracked by the proposed multilateral controller. As you can see on the results here. And the desired object trajectory is also followed, as can be seen in the C3 here. On the right side performs better. C3 is better than C2. C3 is the proposed controller, and C2 is also the neural network-based controller with the direct force transmission instead of environmental parameters. You can see this side is tracking much better. So here it's a state convergence architecture is extended to cover the case of multilateral operation system. So that there's as you can see, once you have let's assume, just use the numbers. You have a K master here and L slave here. The K and the L, the master and the slave, it doesn't need to be equal. Right? So you can have 3 master, 4 slave, or or 5 slaves. So they can be different numbers. So there's lots of parameters. Of course, has to be designed, and conditions has to be satisfied to synchronize this K master and L slave system. So we're not going to go over the detailed math here. There'll be pages and pages of derivations. So I'm going to show some simulation results for the multilateral teleoperation. The simulation conducted using dual master, dual slave teleoperation shows that the reference setup for the slaves are well tracked by slave manipulators. So this showing we have 2 master, master 1 and 2, and then we have slaves, 2 slaves. This is showing the desired. So those are set up, and actually it's you can see in the simulation results is well tracked by the slave manipulators. Here we extend this power-based time domain passivity approach, as I mentioned at the very beginning. So we talk about the passivity approach and also non-passivity approach, right? So the time domain passivity approach for multiple system communication over the time delayed channels. Passivity observers are designed to monitor the negative power, and the passivity controller are triggered to counter the negative power. Therefore, they ensure the stability, right? So the passivity, that's the advantage, but also it's a little bit conservative. So you can ensure the stability much easier. So here's showing we using dual master. So we use omni bundles to act as a bundle. So we have 2 master to control slaves, 2 slaves. And so that's a dual master, dual slave teleoperation. Shows that the slaves that follow the scaled motion for masters according to the authority levels of each master. So as I just as you can see in the today's talk, I only focus on the teleoperation. So that's the idea. You have the master to operate, and then through the channel to interact with the to control the slave, and the slave interact with the environment to carry out the tasks, and then there's a feedback from the interaction. So we mainly focus on this teleoperation system today. In this, we have the proposed all kinds of a new architecture, and there's 3 channels and 5 channels and etc. Also, we also enhance the channels by adding the planner, the estimator, and also the disturbance observer to the system. In terms of the algorithms proposed there, we also using TS fuzzy models, and also we use state convergence neural networks. So there are different control algorithms being also added. In a new architecture, also we include the force motion equivalent force and the composite state convergence architectures. Enhanced version of some existing architectures include the disturbance observer based 4-channel state convergence architecture plus TZ fuzzy modeling based state convergence architecture also presented. Also, we have the extension of the aforementioned bilateral architecture to multiple systems also being reviewed. All of the work we carry out in single master, single slave, and then we can extend that to multiple master and multiple slaves. Some portion we did the simulations using Maglev, and also use Quark, and some portion we use in the hardware experiment using the Omni bundles we purchased. So we use some bundles as the masters and the slave to carry out the experimental studies. So, and showing the promising results. So that's all we covered in today's talk, mainly for the teleoperation. I think that's conclude my presentation today. Thank you all for the invitation. Thanks, Dr. Day, and thanks, Dr. Sabatier for the introduction, and also thanks, Dr. Roy, for attending this talk.
I now request my colleague, Professor Roy, to propose the vote of thanks.
Whether there is any question to sir? Any question from anyone?
In the YouTube, there is no question, but I have one question to Professor Gu.
Yes.
That so many experiments that you have done on bilateral teleoperation. So I just want to know your experience on the problems that you may have faced in the communication channels while transmitting the information between master and slave. The prominent issues, the challenges that you may have faced.
Yes. So communication, there's always issue here. Actually, recently we had I have another symposium I was just organizing. We also invited lots of experts, particularly those experts actually is for the aerospace. So we did in this past couple of decades here, we're doing teleoperation. Most of the study here is simulations, and we simulate the network, simulate the communications. Even here, as you show here, we show here using the Omni borders for the teleoperation. But as you can see, we have the master and the slave is just on the side. We just traveling through a very short network and they come back. So the communication delay in our case is not that far. But if you're going to do aerospace teleoperation, typically the margin is 2 seconds. If you have that in less than 2 seconds, there's many different ways you can use impedance control, some other algorithms, so you can try to mitigate this communication delays. But sometimes the delay will be over multiple seconds. Then it's not that easy. You can use in just a simple control algorithms to do that. Then you have to come up with different schemes. Some planner has to be introduced in both the master and the slave side to mitigate this communication delays. Yeah, so teleoperation, one of the major issue is the communication delay, how to try to solve. There's all kinds of different scenarios. Then you have to find different ways. There's no unique, just one solution to solve all the problem, all the scenarios. So that's why there, here we propose all kinds of different architectures, different channels, showing. So there's I think in the we did lots of this work. Basically from all those from the experience, I think it's when you try to control this properly, there's a scheme is probably integrations. There's all kinds of for different kind of algorithm. There's always pros and cons, at the end of the day, you try to integrate the different algorithms together to to get the the nice part. You keep it. If some part that they do not perform well, then you try to adjust or revise or remove that part. So eventually, you can add those elegant blocks or modules and integrate them together. Hopefully, you can improve the performance of the overall system. Thank you. Hope I answer your question.
Yes, yes, Professor Gu. Thank you. I got my answer.
Professor Subudhi,
Yeah.
if you permit,
So, yeah, please.
if you permit, I will request a small clarification from Professor Gu, because
Yeah, yeah,
we will not get such an expert very frequently. Right?
Yeah, please go ahead. Please go ahead.
So, Professor Gu, what I observed that in your slide of multilateral teleoperation, the time delay for the forward path and time delay for the backward path, both were considered to be same. Any comment on that? Number one. Number two, for the network control system, we have there is again another thing called packet drop. Whether in your whole analysis, have you considered this packet drop? So these are my 2 points. I request you to give your opinion on this.
Thank you. So your first question is asking whether the communication delay from the master to slave and the slave to the master are the same. Is that correct?
Yeah. That is what you have. What I saw in your slide. This is what I saw in your slide. That in both cases you have considered this to be same. Any reason for considering them to be same, or they are usually should be different?
If you're using the exactly communication channel, the natural consumption, of course, if you use exactly the communication channel, because when you're doing this, the communication channel is actually usually the same. The communication is also just a by, right? It's from this side to that side. You're using the same channel. Normally, you assume the speed there is constant. It's consistent. So the delays will be very, very similar. So naturally, you can assume it's similar delays. Of course, the network changes, instantly. So that if you're sharing the network, if you're not sharing, it's a good approximation. You say they're same. If you're using this general network over the internet, then the users on the internet changes all the time, right? So the delays can be different at the instant. They can be up and downs. In some of the cases, we assume they're same. But yes, definitely this can be easily extended to add variations in the both forward and feedback delays. We can change the difference and add that into the control design. What is your second question?
Second part was packet drop. Have you considered packet drop in your communication?
I didn't. We seem I don't recall we had that there, but definitely it's the area we can also consider when we in the future work.
Yeah. Thank you, Professor Go. Thank you.
Thank you, Professor Roy.
Yeah.
So, any other question from the audience to Professor Gu? Because it's very interesting, research he has been sharing with us, and the right opportunity to discuss with him to get some insights. So any more questions? If you are unable, you can put in the chat box also. We can put, or you can take his email ID, correspond to him later on if possible. So if there is no more question, and I take this opportunity to request my colleague, Professor Roy, to propose the vote of thanks.
So it's my
Thank you.
pleasure and an honor to express the vote of thanks. So I, on my personal behalf and on behalf of the organizer of the symposium, extend my heartiest thanks to Professor Jason Gu for his excellent presentation, for sharing all his architecture, all the possible architecture for teleoperation, right? And he basically extended the concept from one-to-one to multilateral teleoperation also. What was very nice in his presentation that most of these things they have experimentally validated. So that is something that has given us a lesson. So I take this opportunity to thank you, Professor Go, for your excellent, informative presentation, sharing all insight with us. I take this opportunity to thank Professor Bigdana Subodhi for chairing the session and finding out his time. I know how busy he is. Every time he has got this or that, too busy man. And I take this opportunity to thank all my colleagues who are here and all participants whom we cannot see, or many others whom we cannot see it here. They are attending it in live through YouTube channel. And in fact, most of our participants, possibly they are there in the YouTube channel. So let me thank all of them for your time and effort, and hope this particular session has enhanced our knowledge to some level on teleoperations of robotics, of robotic systems. So with this, I conclude, and I thanks all of you for attending the session. Over to Rajiv Dey.
Thank you, sir. Thank you, sir, for
Thank you.
supporting us and for your collaboration. And I thank all the chairs, co-chairs, professors who have attended this session. It was indeed a very interesting one. And we come to an end of this plenary talk. We will continue with the parallel technical session in this Google Meet link. Another technical session will start. So I request you can attend our technical session too in this link. And there is one more parallel session on control theory that is going to start. So thank you very much once again to everyone present here. Thank you. Thank you very much.
Thank you. Thank you. Thank you, Professor Go.
Thank you.
Thank you, Rajiv.
Thank you, sir.
Bye. Bye.
So welcome everyone to the parallel technical session 3. So we got a little bit delayed because of the plenary session that was continuing till last minute. So I on behalf of the organizer, welcome Dr. Sandeep Ghosh, Associate Professor, IIT BHU, to this session. And also thank you for accepting our invitation and sparing your valuable time to chair this technical session. I welcome also our co-chairs of today's session, Dr. Manas Bera, Assistant Professor, Department of Electronics and Instrumentation Engineering, NIT Silchar, Dr. Vipin Chandrapal, Assistant Professor, Department of Electronics and Instrumentation Engineering, NIT Silchar. So I welcome you all on behalf of the organizing team Soccer 2020. And I leave it to the co-chairs of this session to start the proceedings of the session.
Thank you, sir. One second. Myself, Dr. Manush Kumar Bera, along with Dr. Bipin Chandra Pal, we are very pleased to inform all the participants that today we have Dr. Sandeep Ghosh, who will be chairing this session. So I will first want to introduce him among you. Dr. Sandeep Ghosh received BE degree in electrical engineering from IIEST Shibpur, the master degree in control system engineering from Jadavpur University, and PhD degree from Indian Institute of Technology, Kharagpur. He is currently working as an associate professor with the Department of Electrical Engineering, Indian Institute of Technology, BHU, Varanasi. His research interests include decentralized control, time delay systems, network control systems, and wide area control of power systems. Once again, I am welcoming you to the technical session 3, and the theme of this track is control application in robotics. So now I will request Dr. Ghosh to take over the session.
So, thank you, Dr. Rajiv Dey and Dr. Manush Kumar Bera for the welcome. And I attended from the morning view of the sessions. So it is a nice organization even in this pandemic mode. Obviously, I hope this session also will go smoothly, and obviously the future sessions as well. So if we come to the session, then this session is technical session 3. It's on control application in robotics 1, and there are 4 papers to be presented. It's almost 2 hours time is given. So since it is in online mode, so we can be little bit flexible rather than fixing timing. So I expect that there will be 10 to 15 minutes presentation, and then 5 to 10 minutes discussions, and adjusting other times it would be around half an hour per paper, so it will be 2 hour session. I hope so. Then so we can go to the presentations as per the sequence given by the organizing committee. Any other point to add, Dr. Bera and Dr.
No, sir,
Vipin, regarding the presentation modes and all these?
No, nothing. Now we can start the presentation as the sequence.
Yeah, I can start. Yes, sir.
So we can go by the sequence as it is given. So first paper is titled Backstepping Based Nonlinear Control of Underactuated 2DOF Gyroscope for Robust Performance Analysis, authored by Monish Patel and Vanu Pothar, and will be presented by Monish Patel. So I would request the author to give a brief introduction, particularly the affiliation, and then start his presentation. So I can see Monish Patel is there. can switch on your video, share your slide, and can start your presentation.
Okay, sir. Thank you, sir. Good evening, everyone. I am Manish Patel. Good evening, everyone. I am Manish Patel from NIT Kurukshetra, a MTech scholar in Control Systems and Engineering. I am presenting on backstepping-based nonlinear control of under-actuated 2DOF gyroscope for robust performance analysis.
Uh, Manish, I think your slide is not shared.
Sir, my slide is shared, sir.
Okay, okay.
Yes,
okay.
sir, it is, sir. So the
But I
flow of
can't.
presentation, yes, sir.
No, it is not visible. You have to you have to
You
share
have
your
to share
slide.
this slide.
Okay, okay, sir. Okay, sir.
Yeah. If in your screen at the right hand
Yes,
side, you
yes,
will
yes,
find
yes.
that present now.
Yes,
Okay,
sir.
that you have to do.
Is it visible now, sir?
It's coming. It's coming.
Yes,
Okay.
yes. Now it is.
Okay.
So you can start from beginning.
Yes, sir. Good evening, everyone. I am Manish Patel from NIT Kurukshetra, a MTech scholar in Control Systems and Engineering, and I am presenting today on backstepping-based nonlinear control of under-actuated 2DOF gyroscope for robust performance analysis. So my presentation will go through first the introduction to the system, then the literature review. Then based on the literature review, we will do the modeling of the system, and then the control objective will be decided. Thereafter, control law will be designed as per the control objective, and the stability analysis of control law, then the simulation results to investigate the effectiveness of the proposed controller. So introduction, gyroscope is a nonlinear and highly coupled system. Hence, the dynamics is one of the most interesting problems of mechanics. We can see here that the gyroscope system find applications in various fields like attitude control of satellites, scanning and tracking in combat vehicles, submarine inertial auto-navigating, actuation of dual-arm space robots, underwater robots, and anthropomorphic test device for two-wheeled self-balancing vehicles. So it can be seen that the gyroscope find application from space to water and in robotics too. So coming to the gyroscope system, I have taken the screenshot of a concert gyroscope. So it has a disc. We can see this is a golden color. It is a disc mounted inside a blue gimbal, which is in turn inside a red gimbal. These are placed inside a silver frame. Okay. So and all the subsystems disc, red gimbal, blue gimbal, and silver frame are fixed with a DC motor and a high resolution optical encoder. Also, 2DF can be achieved by fixing the silver frame, and under actuation can be achieved by controlling the angular position of red gimbal by the DC motor present at the blue gimbal. We are considering the under actuated system because gyros are used in mostly complex systems. So to increase the tolerance for failure of actuators and to deal with space and weight constraints, we are considering the under actuated system. So coming to the literature review, in last few years, we have seen these are the three important papers which have worked on the underactuated 2D gyroscope. First is the feedback linearization and adaptive control schemes with periodic match disturbance by Montoya, and then the sliding mode and adaptive fuzzy control without any disturbance consideration in simulation by Mishra and Sinha in 2019. Sliding mode control to achieve tracking and periodic output disturbance rejection by Toriomi and Angelico. So we can see that the control problems mainly considered are for the disturbance rejection or tracking problems or stability analysis of tracking problems with periodic disturbances. None of the papers have considered the generalized disturbance and the more systematic approach to design a control law. So now we will design the dynamic model of 2D of gyroscope of our system using the most famous, using the famous Euler-Lagrange equation given by equation 1. In equation 1, L is equal to T minus V. T is the total kinetic energy and V is the total potential energy of the system. In our system, there is no potential energy and the kinetic energy of the system is given by equation number 2. So to derive the dynamics of our system using equation number 1 and 2, we are considering psi is equal to alpha, beta, and gamma, where alpha is the angular position of the red symbol, beta is the angular position of the blue symbol, and gamma is the angular position of the disk. So after using the equation number 1 and 2 and psi is equal to alpha, beta, gamma, we will get the dynamics of the equations by equation 3, 4, and 5. On rearranging, we will get the equation 6, 7, 8. As we can see that from equation number 3, we have achieved the under actuation by putting the uh, disk, by putting the DC motor torque or DC motor at rel is equal to 0, and the coefficients of alpha dot, alpha double dot is a function of beta only. Our control objective is to design a control law such that the angular position of red symbol alpha tracks trajectory alpha d. The angular position of blue gimbal beta remains bounded around origin. Also, a controller is to be designed so that the disk rotates at the desired constant angular velocity. Analytically, if tracking array is defined as E is equal to alpha minus alpha d, then E of t tends to 0 and E dot t should also tend to 0 as t tending to infinity, and angular velocity of disk should also tend to our desired angular velocity as t tends to infinity. So control law design. The system considered is under-actuated with actuated shape variables. Actuated shape variables we can see from this equation number 3 that the coefficient of the alpha double dot, which is a under-actuated subsystem, contains only the beta terms. Hence, it can be said that this is the actuated shape variable system. Reza has proposed that backstepping based nonlinear control for such systems like actuated shape variables, backstepping based nonlinear can be used for these systems, but the dynamics should be in strict feedback form. It can be seen that from literature review that the control design for under-actuated 2D gyroscope using a systematic approach like backstepping has not received much attention. So we are using this backstepping based controller, which is a systematic approach to design a controller, and it can be seen following that how extensively it has been used in different systems and different areas in the past, like in the stabilizing pendulum near equilibrium point, in trajectory tracking applications for UAV, unmanned aerial vehicles, output voltage regulations in buck converters, tracking of angular velocity in buck converter fed PMDC, swing up and rejection of uncertainties of card pendulum system. So before designing the backstepping based sliding mode control, our objective was to first rotate the disk at the constant angular velocity. So to achieve that, a proportional controller has been designed to rotate the disk at the desired angular velocity by linearizing this equation number 8. By linearizing equation number 8, we will get a linear dynamics of this subsystem, and the proportional controller can achieve our control objective. Thereafter, we left with the two subsystems alpha and beta, red symbol and blue symbol. So we are designing for this backstepping based sliding mode control. As we know that the sliding mode controller is a robust controller which deals with the uncertainty in the system, and the order of sliding surface depends on relative degree of the system. While designing the backstepping based sliding mode controller, it is not required to calculate the relative degree, but it is beneficial or handy at a time to calculate this relative degree at a later stage. It will benefit maybe. So comment on relative degree cannot be made since tau1 is not explicitly appearing in the equation number 6. As we can see that in equation number 6, tau1 is not appearing explicitly. So taking derivative of equation number 6 with respect to t, we will get the equations 10 and 11. Now we can see that the in red symbol subsystem tau1 is appearing. Now taking state variables as alpha, alpha dot, and alpha double dot. Since these are equation number 10 and 11 are not in the strict feedback form, so we have to convert this into strict feedback form. The system dynamics in 10 and 11 can be written in strict feedback form as given below by 12, 13, and 14, leaving below the internal dynamics of the system to be dealt separately. So in equation number 14, we are seeing a tau d term, which is a matched uncertainty we are considering to check the robustness of the system, the control design. So coming to the backstepping based control design, step 1 is to choose a control variable, which is the error between the output of the system and the required trajectory. So x1 is the output of the system, the angular position of the red symbol, and x1d is the required angular position or required trajectory of the angular position of red symbol. And choosing the Lyapunov candidate in terms of the control variable itself, v1 is equal to half e1 square. Now time derivative will come to v1 dot is equal to e1 dot, and if we will choose x2 is equal as given in this minus k1 e1 plus x1 d dot d, we will get the v1 dot is equal to minus k1 e square. But this is a state variable x2, so we will define a stabilizing function or a virtual input rho2, which will be equal to x2. So we will try to we will try to tend this x2 towards the r2. So there is a next error e2 x2 minus rho 2. So we will try to stabilize this e1 and e2 to be asymptotically stable around to origin. So we will calculate the errors, and we will choose the Lyapunov candidates in this sequence till we will get the our control input explicitly in a time derivative of our error. As we can see in the equation number 21, E3 dot contains control input explicitly. So we will stop here, and now we will design the sliding surface. The sliding surface is taken as E3 plus C1 E2 plus C2 E1, where C1 and C2 are the control parameters which can be chosen as per the control engineer. So now another Lyapunov function we can to include the sliding surface v2 plus half s square. Using equation number 20, 21, and 22, and the e2 dot and e3 dot, we will get the v3 dot as given in equation number 24. Now we are using the conventional constant plus proportional rate reaching law given below will be used to design a control law. S dot is equal to minus q signum s minus ks. By using the equation number 24 and 25, we will get a control input v, which tau1, which is given in the terms of v as given in equation number 27. Control law 27 will achieve our control objective, that is e1 dot t will tend to 0 as t tend to infinity, and can reject bounded continuous matched uncertainty disturbance by choosing q appropriately. We will see in the stability section how we will choose the q and what should be the range of the q to stabilize the system asymptotically. Now I have considered a term in this control law, adaptive estimation of match disturbance. Here we are estimating the disturbance using a variable d hat. So d hat is estimating the disturbance, and the error between the estimation and the actual value of this disturbance is given by our error d tilde, which is defined by equation number 28. Now we also require that d tilde should also tend to 0 as t tend to infinity. So we are defining a new Lyapunov candidate, v4 is equal to v3 plus 1 upon 2 gamma d tilde square, where gamma is the adaptation gain, and it can also be designed by some optimization technique or by the control design engineer only. On solving this equation, we will get the v4 dot as given in equation 30, and to make v4 dot less than is equal to 0, we are getting the adaptation law as given in equation number 31. Now coming to the stability analysis. In stability analysis, we are using the Barbashin-Krasovsky theorem, in which there are three conditions to be satisfied, so that we can infer that our system or state variables considered in the Lyapunov function are globally asymptotically stable at origin. So our Lyapunov function without disturbance estimation is given in equation number 32, which satisfy the equation number 33 and 34. Further, we are left with the one more equation, v3 dot should be less than 0 for all e1, e2s except at origin. If it is proved, then we can infer that e1t, e2t, and st are globally asymptotically stable, and hence our system is also stable. So if we will calculate, then we will get v3 dot as given in the equation number 35. And supposing there are two matrices E, which contains the three errors of the backstepping based controller, and we are putting norm of S1 tau bar D in place of S tau bar D, since we know that the norm of norm 1 of any signal is always greater than or equal to norm of any signal for any p greater than 1. So V3 dot can now be written as in equation 36. To make the V3 dot less than 0, our P matrix should be positive definite and Q should be greater than tau d bar. So from here we are getting the condition for the Q parameter, and matrix P can be made positive definite by choosing the C1, C2, K1, K2, K and Q appropriately. Now we are going to see the stability analysis with disturbance estimation term. So in this we can see that the E and P matrices are same as given in before, but we can see from equation number 40 there is no condition on parameter Q, which is advantageous as compared to the conventional part, and we can make the P positive definite as given as in the previous system, as in the previous slide. Now coming to simulation result. Before simulation result, I should say that the stability analysis of blue symbol can also be can be done by considering by considering angular position of the red symbol is tracking the desired trajectory alpha d, and disk is rotating at the required angular velocity gamma d, which we have already achieved. And linearizing that dynamics of the angular position of blue symbol comes out to be first order linear differential equation, and then can be solved using the integrating factor method. Beta d comes out to be bounded for bounded reference trajectory alpha dot d. Simulation results, we have considered the alpha d as given in this, and gamma dot d as 34 radian per second. We have considered a matched disturbance as a Gaussian function, and x is a Gaussian variable. To reduce the chattering effect, we are considering tan h instead of signum function. Moment of inertia of the constant gyroscope we have considered in our system to simulate it, and controller parameters are calculated using the trial and error method. So it can be concluded from the result that the proposed controller, as we can see from the figure 2 and figure 3, the angular position of the red symbol is tracking our reference trajectory, and eliminating and rejecting the disturbances, and blue gimbal angular position of blue gimbal is also within bounded. It is between the 1 degree and 2 degrees. Control input of control input with matched uncertainty for disturbance estimation is having less chattering as compared to the conventional BSMC. It can also be evident from the sliding surfaces. Now we are using the Monte Carlo simulation design to check the unpredictable interaction of unmodeled dynamics and uncertainty, which is not investigated or commented upon the previous literatures. So we are using the Monte Carlo simulation method with random uncertainty already considered, and to test the robustness of the proposed control law. The system is simulated for 40,000 instance of time, and histogram of the tracking error is plotted. From the table 3, we can see that the mean tracking error is lesser for the disturbance estimation, while the control input is more or less same. Now we have plotted the histogram.
Manish,
Yes, sir.
I'm interrupting. So
Yes, sir.
it's almost 18 minutes for this
Yes, sir.
presentation. So
Yes, sir, it is
wind
about
up
to finish.
it within 2 minutes or
Yes,
so.
sir. Yes, sir, it is about to finish. Yes, sir. And from the histogram of the tracking error, we can see that for the conventional backstepping based sliding mode control, it is concentrated near the 0.21 or 0.22 degrees, while for the disturbance estimation, it is concentrated most of the time at 0 degrees. The conclusion: a backstepping based nonlinear robust controller has been designed for 2D of under-actuated gyroscope and validated in the simulation environment. Upper bound of match disturbance is not required with adaptive estimation in the controller design. Monte Carlo simulation method shows tracking error is closer to 0 at most instances of the time for the proposed controller, and lesser controller effort is required, or it can be said that more or same it is same. Future scope is improvement in performance using intelligent control, estimation of state variables. It can be used in the different robotic applications, and controller design in discrete domain to be used in digital computers. These are my references. Thank you.
So thank you, Monish, for the nice presentation. So
Thank you,
this is the paper is now for discussion and
Yes, sir.
questionnaires. So any question from the audience? So you can write in the chat box if you have any question, or you can speak.
Okay, Manish.
Yes, sir.
Okay, Manoj, sir,
Yeah.
please.
In your case, I have seen that you have used first order sliding. Means
Yes, sir. The second order sliding
no,
surface I have used.
no, first sliding. First sliding you have used. Well, conventional sliding you have used.
Yes, sir.
So here it will work on relative degree 1, and I can see that for the output what you have taken the relative degree is 4, something like that. Some expression I saw in your presentation.
Yes, sir. This is relative degree 3, alpha triple dot.
So for implementation of this conventional sliding, you need any more information, like more derivative of the state variables?
Yes, sir. Sir, I have used the sliding surface of second order as given equation 22.
So for that you require the derivative of the states.
Yes, sir. Yes, sir.
So how you have
Yes, sir. If
calculated?
we will, yes, sir.
How you have implemented? When means if the
Yes, sir.
derivative is required, then
Yes, sir.
how?
Yes, sir. If we will use, if we have to put into the real time implementation, then we have to use the high pass filter.
So do you think that the high pass filter will be
No,
sufficient to reconstruct the
no,
derivative
sir.
of a noisy signal, because you have the disturbance also?
Yes, sir. Yes, sir. Yes, sir.
So do
So
you have ever thought to how to tackle this situation?
yes, sir. That's why I am before implementing in the real time, I was
Mhm.
thinking of estimating the error, estimating the derivative signals before implementing for the real time.
Okay, so
Because in
having
that case, we have to calculate only the output variable, which can be calculated by the positional encoders present on the uh, system.
okay, so now these are the simulation results. You have not implemented till now in the
No, sir, not in the real time, sir. So we
okay.
have
These
just
are
set up in the lab. Yes, sir, we have
yeah.
set up in the lab, but we are not able to implement in the real time right now.
Okay, okay.
Yes, sir.
That is from my side. It's okay,
Yes, sir.
fine.
Yes, sir.
Anyone else want to ask, please?
Thank you,
Yes.
Manoj, sir.
Okay.
Mhm.
Okay. Thank you, sir.
Yes,
Yes,
Vipin.
Manish, I have one query regarding your presentation. Although your
Yes.
presentation
Yes,
is very good,
sir.
actually you have discussed that you have considered some disturbances.
Yes, yes, yes.
So, but in the simulation result, any
Yes, sir.
type of disturbances has not been shown. That means which type of
Okay, okay.
you have considered.
Okay, yeah. This is a Gaussian. I have written only the equation. So it is actually a random number generated. I have in the graph of this disturbance in my paper. I have not included in this PPT.
Okay, you have generated a random Gaussian variable as a
Yes, sir. Yes,
noise
sir.
with
Okay.
zero mean and two
Yes, sir.
variance, right?
Yes, sir. Yes, sir. It is included in the paper.
Okay. Okay. Thank you, Manish.
Okay.
Thank you, Vipin,
Thank
sir.
you.
So, anyone else having any question? Okay, I have a
Yes, sir.
question, Manish. It's regarding the question asked by Dr. Manas Kumar Beda.
Yes, sir.
So it's regarding the same topic or related to implementation. So
Yes,
how
sir.
you implement that X triple dot that you are using for the controller? So it's that you have to use a filter, and
Yes, sir.
obviously you will do digital implementation. So digital issues and the issues related to discretizations will be there.
Yes, sir.
So, do you think that the errors associated with uh, calculating the derivatives of the states,
Yes,
can
sir.
those be correctly represented as matched disturbance that you have considered?
Sir, that cannot be represented by match disturbance. It will come as the mismatch disturbances in the system because that
Okay,
these are not entering through the input.
Exactly. So then only the match disturbance can take care of your error in implementation of the control input.
Yes, sir. In the control input and the disturbances or the uncertainties given by the DC motor, torque provided by the DC motor can be considered only by the match disturbances.
Only as the match disturbances.
Yes, sir.
Okay. Then what are the cases for mismatch disturbances and how that can be taken care of?
So in my control law design,
Yes.
okay.
So will
So
it be able to tolerate even a smaller amount of mismatch disturbance?
Yes, sir. It can tolerate the parametric uncertainties and mismatch disturbances also.
Okay, so have you done that
Yes, sir.
analysis
Yes,
up
sir.
to
Yes,
how
sir.
far this mismatched uncertainty can be tolerated for this case?
Yes, sir. I have considered the parametric uncertainties till 5% individually, and the overall it was coming around 10 to 12 percentage. If I am considering the 5% deviation from in all the measured moment of inertia, so I have considered that while simulating the results.
Okay, okay, thank you. So that's all from my side. I hope anyone else having any question, any more question? Okay, then thank you, Monish, for the nice presentation. Thank you.
Thank you, sir.
So we'll move to next presentation. Next presentation, it's titled Adaptive Backstepping Based Non-Singular Finite Time Sliding Mode Controller for Suspension of Maglev Platforms. Authored by Navnita Odhikari and Jovin Matthew. And it will be presented by Navnita Odhikari.
Thank you, sir.
Okay, over to you.
Thank you, the chairs and co-chairs of the session. So I'd like to our paper is titled Adaptive Backstepping Based Non-Singular Finite Time Sliding Mode Controller for Suspension of Maglev Platforms. I will be presenting the paper. My affiliation is currently, I'm the assistant professor in the electrical engineering department of NIT Silchar. And the other author, Mr. Jovin Matthew, he is the assistant professor in Assam Engineering College, Guwahati. So now moving on, the paper mostly presents the designing of a sliding mode based control system for a maglev platform that is used for transportation methods. And here is the outline or the overview of my presentation. So why choose maglev platforms is because maglev platform they did gain quite a popularity when they started, but because of their lower energy consumption, their noise-free operation, as well as they have high riding quality as compared to the other modes of contact tractions. But the issue with the maglev platform is that they are inherently non-linear and they're highly unstable. And also when we are dealing with large transportation containers and such containers or bogies, then for such a huge system, the controller will have to be extremely stable. Otherwise, it becomes a safety risk. It becomes a hazardous situation. So, in searching for different kinds of controller that have been developed for maglev platforms, most of the older controllers that have been developed where the authors mostly concentrated on PID type of controllers. And then as the robust controllers came into pictures, SMC, H Infinity, and all those different kind of robust controllers have been tested on such platforms. The sliding mode control, as my previous speaker already explained, it has the very good advantage of being a highly robust controller, but also it has the disadvantage of not being able to tackle mismatch uncertainties, and also there are some issues when we encounter when a relativity of the system do not match. And So, but the thing is that the sliding mode controller can be combined with other methods. So backstepping is one such a method with which we can combine sliding mode controller that sort of gives us a structured method to or a structured steps to find out the final control input or the expression for the control input. Also, along with the sliding mode controller, if we include an adaptive tuning of the controller gain, then that actually allows us to tackle the uncertainties better than choosing a constant gain. The disadvantage of the sliding mode controller is that although due to the very high controller gain and its robust nature, we can choose a high gain and simply force the system to act as we want. But that high gain value also leads to, as we know, the sliding mode controller leads to chattering, and the high gain value also leads to higher amount of chattering, which is extremely undesirable. So in order to tackle that, this adaptive tuning of the controller gain can help us in lowering the amount of chattering present in SMC. Coming to the structure of the system and its model, so the Maglev platform, the modeling of the Maglev platform, it has been collected from this paper reference 7. So the entire huge platform, it is divided into 4 parts, A, B, C, and D. And on the 4 parts, so we will be mostly concerned with these motions. One is the angular motion by the y-axis here, another is the angular motion by the x-axis in here. Then the motion, linear motion along the z-axis, and also the rigidity of the platform. If it twists and turns, then this is not good. So we want to maintain the platform at a rigid level. So these are the 4 states that we'll be concerning us with, and in all the 4 controlling the 4 states, we these are the control forces FA, FB, FC, and FD, and they're linked to the currents that are passing through the coils of the electromagnets. So the rest of the expression terms that you see here, WT and LT, these are the length and width of the platform, and ZA, ZB, ZC are the linear displacement along the z-axis for the 4 parts of the platform. Now, so this is simply the description of whatever I showed you in the previous slide. Now, the important thing to note in here is that, as I told you, that maintaining the rigidity of the platform is also one of the objectives. So it means that the ZA, ZB, ZC, and ZD, they should all move at the same time, and there should not be the changes in the movement of the Z, A, B, C, and D should not be different. Otherwise, we will lose the rigidity. As we know that the force developed in an electromagnet is linked to the current by this equation 1. And as you can see, this is a nonlinear relationship that we have. And this term GE, this is a time varying coefficient. So due to this, P is a flux, and due to this derivative of the flux, due to this presence of this term, we have a time varying coefficient, we have a nonlinear relationship. So as we can, and what we can do is that the entire motion for all this platform, it can be written in this format. So M naught, it represents all the mass and inertia terms. D naught basically represents the forces due to gravity. So the rest of the which is going to only affect the position along the Z direction. And UC are the control inputs. So UC are given by, so here we have these coefficients, they're time varying coefficients multiplied by F, and this F and U is actually the currents, so they are related by these coefficients. So without going too much into detail of this modeling here, what we can see is that the Maglev platform can be modeled in this format, and from this format we will try to find out the control input expression. So now, as I told you before, that the position vector, the state vectors for the system are the motion along the z-axis, the angular motions, and this kappa actually it represents the rigidity of the entire platform. So we do not want this kappa to change. It should remain constant. So that would mean the platform will remain rigid all the time. So now, so obviously, as we know that whenever we do mathematical modeling, we cannot do the accurate modeling of the system. We always end up with having some kind of an approximation of the system in our model. So whatever is left out of that approximation, that we can consider that to be our parametric disturbances. So what we have done here is that this delta M and delta D, these are those terms that we were not able to actually include in our model. So these are our parametric uncertainties or the parametric disturbances. And FT is some disturbance that is some external disturbance that is acting in the system. So including all the disturbances and all the nonlinearities, this is the final equation for the Maglev platform. Here, these two terms are already explained. This LU terms come because of the disturbances. So we have considered that we have lumped all the disturbances into this LU vector, and it is given by this delta M x double dot plus delta D plus FT. Now, one assumption here is that all of these disturbances are bounded. Whatever external disturbances are acting on the system, it is bounded. Anything internal that's happening, they're all bounded. Nothing goes out of limit. So this is one consideration we have to keep in mind before designing our control law. Based on the discussion on the model and limitations of the model, so these are the main objectives of the controller. So since we have a nonlinear relation between the force and the current, so obviously we'll end up with a highly nonlinear system. So we need to tackle that. As we know that in Maglev system, we have inherent instability in the open loop. So that is another thing that we need to take care of. And also the controller currents, and we can see that we have time variant coefficient. So now we have a time variant nonlinear system. So automatically it becomes designing the controller, it becomes a challenging task. So now so based on that, so we have put some objectives while designing the controller. So as we know that for any system, we always define some kind of system performance, desired system performance. And based on that, and those objectives can actually help us in finding out the controller parameters, the controller structure, etc. So first objective is that we need a very low overshoot, because if we are to use a Maglev platform for a transportation, then we cannot end up having very high overshoot every time some small disturbance affects it. The second thing is that the settling time, in addition to settling time being fast, it should also be smooth, because we are talking about transportation. If you think about even transporting people, so in that case, any slight disturbance and then the settling time, if it's jittery, then that is going to be uncomfortable, or that is again going to be very, very dangerous. The third objective is achieving finite time convergence. And then the fourth objective is to obtain the desired performance without use of any excessive input energy. So as I told you before, that SMC due to its switching nature, we automatically has the disadvantage of chattering. And in addition to that chattering, if the magnitude of the chattering becomes very high, then it's kind of a lossy process, and it is very impractical. So we need to lower, if we are able to smooth out the chattering in the control input, then we will automatically use less amount of input energy to do the same amount of tasks. So now, coming to the controller design process, we are using backstepping with sliding mode method. So the first step involves, as we know that in backstepping, we start at the output. So we start at what we require. So what we have some desired trajectories defined for all the states. So we will start there, whether we are at the desired trajectory. If we are not, we will define that as the error between the two. And then we have defined the first regulatory variable for the backstepping as the integration of this error. And then again, this equation 8 is the differentiation of the equation 7. And now we are going to consider this equation 8 as an isolated system. And we'll assume that X is the control input for the system. And based on that, we will design a virtual control input, alpha 1. And if we replace x equal to alpha 1 in this equation, we will end up with a stable system. So this z dot is equal to whatever equation we have on the right hand side. If it leads to a stable equation, it means that z will go to 0. Z going to 0 will mean that our error will also uniformly converge to 0. So this is something that we have done. We have defined alpha 1. So we took the help of a candidate Lyapunov function in designing alpha 1 in here. But the thing here is that we assume that x is equal to alpha 1, but this is not true yet because we have not applied any kind of control input. So in order to make that true, we now need to make x equal to alpha 1, which leads us to our second regulatory variable, which is the difference between x and alpha 1. Now, following the same steps as the first step, we are going to define another isolated system here, and here we are going to consider x dot to be our virtual input, and based on that, to stabilize this system 13, we are going to design another virtual control input alpha 2, which when x dot is equal to alpha 2, our system will be stable. Now what we have done here is that instead of choosing a constant controller gain, in alpha 2 we have included adaptively tuned gain. And this gain is tuned based on this equation number 16, where we can see that I'm very, very sorry. This should have been K1 had dot. So this change in the gain, it varies according to the magnitude of Z2, which is nothing but the system error in terms of the position and its velocity. And the second term, this gives us a leakage term. And this term is present to actually limit, to prevent the gain from going unbounded. Now, following this, now as we have already defined some alpha 2 here, now we again need alpha 2 to be equal to x dot, and based on that, in the third step, we are defining the third regulatory variable, which is x dot minus alpha 2. Again, we have defined another subsystem to stabilize this regulatory variable. But this time, instead of following the similar method as the previous step, we are going to define a non-singular terminal sliding surface. So here, as you can see, the surface is a function of Z2 and Z3. And as we have seen from the previous slides, Z2 and Z3 are functions of the system error and the derivative of the error. So now we have a sliding surface, which is a function of the tracking errors. And also this beta and delta are user-defined constants, and the conditions for beta and delta are beta should be greater than 0 and delta should be in between 1 and 2. So this is our sliding surface, and there is a slight modification we have done in the sliding surface, because if we, in order to avoid any complex number situation in the because Z3 might become less than 0, so in that case this term might cause us problem. So in order to avoid that, we have redefined the sliding surface given by equation 20, and the derivative of the sliding surface is given by equation 21. Now, our aim is to design a control laws that will bring the system states from their initial condition to the sliding surface, and the proof is actually given in the paper that the sliding surface is a stable surface, and once they reach on the sliding surface, they will slide along the surface to their equilibrium position. And in order to do that, this is the control law that we have defined. As you can see that this is a model dependent control law. We are including the MDGS terms in the controller expression, but we also have these two terms. So the signum as this term represents the switching function for the sliding surface, and this W into S term is present to smooth out the chattering in the system. So this comes actually from the reaching law method of designing the sliding mode controllers. And again, once again, here the controller gain for the switching part of the controller, it is tuned adaptively based on this adaptive tuning law given by equation 23. And as you can see here, the gain variation, it depends upon the value of the sliding surface or the sliding parameter, sorry, not the sliding surface. It depends upon the value of the sliding parameter. And it also depends upon the value of the last regulatory variable defined Z3. And this middle term, it is the leakage term, which prevents the controller gain, this adaptive tuning law to make the controller gain become unbounded. So now so based on this, we have we are now to design. We have designed a control law, but we also need to figure out what should be the coefficients of the controller. So in order to do that, we have put forward certain lemmas in our paper, and based on these lemmas, this is the first two lemma 1, then this is lemma 2. As you can see, this lemma deals with the first design parameter C1. Then we have lemma 2 that deals with the design parameter K1, which is related to the adaptively tuned controller gain. Then we have lemma 3, which deals with K1, epsilon 1, and gamma 1, which are related to the adaptive tuning with the first controller gain. Then we have the fourth lemma, which again deals with the so here I think I missed one thing. This should have been K2, so it deals with K2. And then we have this final lemma. As you can see here, in the final lemma, we have defined that the entire system will be stable if we can select our controller coefficient so that this equation 27 is satisfied. And in 27, all of these terms, they actually come from all of these terms, they are actually coming from by using Babelet's lemma as well as the Lyapunov function in the system. And we have done a stability analysis based on that, and that has given us all these conditions. So based on all of these conditions that we have derived, we can find out at least even not the pinpointed value, but we can find out certain ranges for our controller parameters. Now, let's come to the numerical simulation. So we have simulated the entire system for a platform having these parameters, and the parameters for the electromagnets are given in here. And the controller, what we have done is we have compared the performance. Since we are proposing two different adaptively tuned gain, generally this adaptive tuning of the gain is done in the final step where we generally have the signum term. So we are going to compare what happens if we choose one gain constant and one gain is kept is adaptively tuned. In this, I'd like to remark that we have got comments from the reviewers that we can probably do a comparison with a recent paper. This is something that this is a controller that was actually designed by us in a previous paper. So what we will be doing in the revised version of the paper is we will select a paper from a recent time and we will compare our results with them. But till then, this is what we have shown in our current paper is this. So we are going to compare the performance of our controller with this control structure, and it is applied to the system. So now these are the parameters that we have used for the controller. So this is for the one that was previously designed controller, and this is for the controller that we have designed. Now, these are the results that you can see here. I'm very, very sorry for this mistake here. This should not have been 49, it should have been 28. But anyway, as you can see, this blue line indicates when we have only one adaptively tuned controller gain, and this red line indicates when we have both the controller gains tuned adaptively, and the green dotted line represents the reference. So as you can see here is that if we select if we choose to adaptively tune both the gains, the performance actually improves. And in this simulation, what we have done is that we started with some initial condition, and then at t equal to 6 seconds, we gave some disturbance to the system, and we saw how long it took it to recover from that disturbance. So as you can see that with the proposed method of adaptively tuning both the gains, the settling of the disturbance also is quick, and we do not get a very high overshoot. The overshoot here is very, very low. Then coming to the input, as you can see here, again, the blue line indicates the controller that we have proposed, and the red dotted line is the previously designed controller. In terms of control input, for the initial part, the previous one, it uses a bit more of it, but as we can see, we have to do some kind of compensation for this better behavior in terms of the state trajectory. So that compensation comes in terms of the control input. So our proposed controller uses slightly higher input than when we do not use all the adaptively tuned controller gains, and this is reflected in this position at t equal to 6 seconds in all the values. And in these simulations, we did not incorporate any disturbance to the system, but then we did another set of simulation where we applied some noise, measurement noise throughout the simulation from t equal to 0 seconds to t equal to whatever seconds we considered our simulations to. And we tested how our controller behaves in presence of all this measurement noise. The noise was present in the measurement of the displacement, and we can see that the controller more or less behaves well. Even when we give some disturbance in here, it's able to settle it back down, so we are not having problem with any of that. And these noise are actually the reflected measurement noises. Now, and corresponding to that, these are the control inputs. They're shown here. If we compare with the previous noise-free inputs, they're more or less the same values in here. But obviously, we have some amount of chattering that because the controller is not trying to deal with, or it is trying to nullify the noises in the measurement that are entering into the system. And these are the adaptively tuned gain for all the 4 parts of the platform. So as we showed you in the starting slides, the platform is divided into 4 parts, A, B, C, D, and we are designing for each of the parts. So these are the adaptively tuned gain. As you can see here is that initially when we are away from the sliding surface, the gain is high, and as we reach near to the sliding surface, the gain becomes lower. And this is the part where we applied some disturbance in ZA in the A section of the platform, so that because of that we are having this change in the gain value, and same thing you can see in the second part also. So now we have come to the conclusion of the presentation. So
okay, Dr. Navnita, so I
yes.
expect we'll finish within 1 minute or so. Okay.
Yes, so this is the final slide, sir.
Thank you.
So we have designed such a controller and we showed that if we can incorporate more adaptively tuned gain into the controller, it actually helps us in improving the performance. And we can use it for this Maglev platform system. As a future scope for this research, we can actually do a thorough analysis for any possible bifurcation in the closed loop system, as well as formulating more stringent criteria for our parameter selection. That is all. These are my references. Thank you.
So thank you for the nice presentation. So I will ask to the audience if they have any question on the presentation. And also Dr. Beda and Dr. Pal.
Now, our audience are very shy, I think. They are not.
Yes, true.
Navnita.
Yes, sir.
It is a very good presentation. And thing is that what happened at 6 seconds? Why there is a jump?
We applied a disturbance at 6 seconds, sir. Here
Okay.
we applied a disturbance here. We just applied a step, kind of impulse kind of disturbance in the position in the Z direction.
Okay.
Yes.
And you are using that terminal sliding mode to have the finite time reaching, means
we were aiming for that, yes, sir.
Yes.
But the thing is that we actually had to modify it a bit. I mean, I don't think this will yield us absolute finite time reaching here. Because if we use terminal sliding surface, we could have got that, but we cannot use that. We have to go for non-singular terminal sliding.
Okay. So for your design, is it possible that suppose if I will fix the time, and then if you want to calculate what will be the gain, that gain of the controllers when a controller design, is it possible for your case, or
we could not do that. Actually, we were aiming for that, sir. But since we have this 2 to the power delta term, and choosing this terminal sliding would have given us that, would have made it possible. but we faced a lot of issues, and I think we were not able to do the calculation. So we ended up with non-singular terminal, and so then we do not have the finite time convergence.
And your control looks smooth. Why?
Yes.
I mean, why your control for which part in the control? Because you are using sliding mode, but still your control looks smooth. Why it has happened like that?
So pardon, I
mean, in your, if I see the control is continuous.
Control input.
Yes, yes.
So what you did with your control that it become, though you are using sliding mode, but it become continuous. How it has happened?
Yes, sir. Actually, there are two things. One is we have added this when we do the reaching law approach. This WSC term, it actually takes care a lot of the chattering from the sliding mode control. So this is one of the reasons. And another reasons is that we have also used this adaptive tuning of the gain. So what happens is that when your system is, say, very much away from the sliding surface, at that time our gain values are high, but then once the system settles, the gain value becomes very low. So we may have chattering, but the chattering amount of chattering is very, very, very low, that we can ignore it. So that's what's happening here actually.
Okay, thank you.
Sorry, I'm interrupting in between. This left-hand side, these currents are the inputs, right? Both left-hand and right-hand side, right?
Yes.
Okay.
This is the forces, and these are the currents corresponding to. They're related by that law.
Yes.
Yes.
Forces and these are currents. So we can see that the scale of the forces or the input that is very high. So there might be chattering. So you have to zoom in.
But it is not visible.
Yeah, it's
yes,
not
sir, there is chattering, but compared to what the system that we are working on, though that chattering are very small, like based on the magnitude of the input, the chattering is very low. Yeah, I could have, yes, I should have magnified that part actually.
Okay. Yes. If you could have given a zoomed portion from that chattering, then it would be visible.
Okay, so, Sandeep sir, it is done from my part.
Okay. Okay. Thank you, sir. Then any other question, Dr. Pal and
No,
others, audience?
I request to audience, if anyone have any query, then he can ask.
Yes, even you can write down in chat box. Okay. So I have a question. Regarding the particularly the adaptive gain. And its leaky gain implementation.
Yes, sir.
So that epsilon 2 actually epsilon 2 that ensures how the K2 hat will be around the desired gain value, right?
Yes.
And that epsilon 2 that might play a role in how closer it is near to the sliding surface.
Yes.
Right. So
yes,
if epsilon 2 is chosen high, obviously then leakage will be high, and your control gain will be means away from the sliding surface, means there could be more width in the variation in the sliding surface, or when it reaches the sliding surface, there it can take more width. So that could be one reason for that you have less chattering. So you can find out the actual reason.
Yes, 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 sir. That is a very good point.
And what is that epsilon 2 value you have chosen?
It's very low. I think I chose it to be 0.001. Generally, these values are chosen very low.
Yes.
Yeah. This is 0.001. Both the values I have chosen as 0.001.
Okay. It's because the chattering is so important in this application, particularly
Yes,
when
sir.
you are using a current fed magnets as actuators or electromagnets as actuators. So you are basically regulating the current or it's the input to your system. So regulating current at very high frequency is very difficult. Okay.
Yes, sir.
So you have to keep that in mind, particularly for application, that there should be as minimum chattering as possible. If you go for implementing sliding mode control, obviously, if you go for other things, then regulation point or chattering problem won't come. Okay. So
Okay, sir.
that could be one issue regarding implementation, that current regulation will be very difficult.
Yes, sir.
Okay. Okay, so that is all from my side. So still, if any other questions are there, you can raise. Okay, then we can move to next presentation. So thank you, Dr. Navneeta, and I
Thank you,
think
sir.
you will present the next paper as well.
Yes,
So
sir.
I would request Dr. Manoj Kumar Bera to coordinate with this presentation. Dr. Bera. Okay. Okay. So
Sir, just a minute. I am calling, sir.
yes. No, Dr. Pal, you can coordinate this one.
Okay.
Yes,
Thank you.
taking a break. Okay.
Okay. Thank you, sir.
Thank you.
Thanks a lot. So now I call for another paper, that is paper ID 59, and the title is Adaptive Robust Control of Teleoperated Master-Slave Manipulators with Communication Delay. And presenter is Navneeta Adhikari, ma'am. So please start your presentation.
Thank you, sir. So this in this work we are actually, this is a part of our Spark project work. So we have we're trying to design a robust control methodology for telecommunication robots. And here's the outline of my presentation. So first of all, coming to the introduction, why telerobotic systems are important, because now with improvement in technology, improvement in internet connections, it's becoming more and more easier to connect between the two corners around the world. And so telerobotic operation, they can actually help us in remote surgery, robotic rehabilitation, disaster management, all that, etc. However, controller designing for such a system is a challenging task, because we have to deal with non-linear robot manipulators, and moreover they are placed in different parts. They're connected by some communication channels which may have delays, and then it keeps on adding to the complexity of the control problem. So some of the recent works that some of the most popular controllers that are used in the bilateral teleoperating system are robust controllers, fuzzy logic, neural networks, and adaptive controllers. And what we are trying to do is we are trying to design an adaptive sliding mode based controller for a teleoperated system in presence of communication delay. So this is our first and the preliminary work. So in here we have considered two robots, one master robot, one slave robot, and they are connected via some communication channel. So the M in the entire presentation, this M subscript will represent anything related to the master robot, and S subscript will represent the slave robots. And these are the dynamics for robotics for the both master and the slave robotic systems. So here these represent the inertia terms, these represent the Coriolis and the centrifugal frictions. They are the gravitational force terms. UM and US are the input torques to the system. Tau H and tau E are the external torques or forces that are encountered by the robot arm, and DM and DS, they represent the disturbances in the system. So before designing a controller, we have considered certain assumptions. The first assumption is that all the joints for the manipulator are revolute. The second assumption is that all the parametric uncertainty and the disturbances are bounded. The third assumption is that whatever external forces or torques are there, they're all bounded, or the interacting forces and the interacting and the torques resulting due to the interacting forces are all bounded. The fourth assumption is that the joint position, acceleration, and the velocity, they're bounded. And this is not actually an assumption. It actually comes from the mechanical structure of the system and its actuator limits itself. And the fifth assumption we are considering for this particular work is that on the slave side, there are no interaction with the external environment. Then again, we also have to consider certain properties of the robot arm. The first property is that the inertia matrix of the arm is bounded, symmetric, and it's positive definite. And the second property is that the entire manipulator system is passive. Now here is a block diagram of the system that we are proposing. So on one side, we will have master manipulator. So whatever position and velocity information of the master manipulator are there, what we want to do is we want to synchronize the position of the master arm to the position trajectory of the master arm to the trajectory of the slave arm. So we will be feeding the information from the master arm to the slave arm controller, but since they will go through a communication channel, there will be certain delay in there. Similarly, whatever slave arm trajectory are there, we will feed them through the communication channel into the master arm. And what we will be doing is we'll be applying a certain force at the end effector of the master manipulator or the hand of the master manipulator, and we will move the manipulator arm. And that will create these movements, and which we want to be reflected in the slave arm side. So this force will be applied to the master arm and end effector, and this force will also be, information about this force will also be conveyed to the controller in the slave. Now this is what we are considering. On both of the sides, the tracking error is now, since we have some delay in the communication, so at the current time instant, whatever we have on the master side, from the slave side, we will have the delayed information. So the error is now the difference between the current information and the delayed information. So these are the error in position, and these are the error in the velocity tracking. So our aim is now to try to make this error zero, or try to make them zero asymptotically. Now, the objective of the entire controller here is that first one is that the motion of the master will be directed by the external force applied by the operator, and this motion will be followed by the slave manipulator. And the second objective is that the tracking errors, they should converge to zero. So what we'll be doing is that we'll design an adaptive sliding mode controller, and the sliding surface will have a proportional integral derivative type of structure, so that we can incorporate the integral of the error into the sliding surface in order to hoping to get more accuracy in tracking. And since there will be communication delay, it will also going to cause us some complexity in designing the controller. So this is what we're going to do, is that first of all, we have defined a variable which is a function of the position error and the velocity error. And this variable sigma, we will define it for both of the controller, master and the slave. This I indicates for master and slave both. So this variable sigma is now used to define the sliding surface on both the sides, on the master side and the slave side as well. And the sliding surface is defined like this. So one portion, the integration of sigma is used in here, and the other portion we are using is the velocity error. When we do that, so this gives us, when we do that in the equilibrium position, when S dot is equal to 0, it leads us to a PID like structure. And this also ensures that our error will converge to 0 as t tends to infinity. So here, this was our sliding variable that we defined. So on the sliding surface, our variable is equal to 0. This is the definition of the sliding surface. And if we expand it, this is what we obtain. And here, what we have done is we have considered Z1 to be integration of EM and Z2 to be EM, and this entire system can be now written as this system given by equation 14. So from here we can actually select the controller parameters. We have to select the values of C1 and C2 such that this system is stable. Otherwise, our entire process will not yield any result. So this is the condition. This is something from where we can design our C1 and C2 values. Now on the master side, this is the controller that we have designed. This is a model-based controller, so all the nominal information of the information of the nominal model of the robot arms are present on the master side, and this part, signum of SM, this part represents the sliding mode part, and this term is there to reduce the chattering, and then this actually comes from making s dot is equal to 0, and then we equate those terms, and then we end up with UM. Now on the slave side, now what we considered, one assumption was that on the slave side there is no interaction forces. So any force or torque information from the slave side is not present in the master controller. But since on the master side we are moving the master manipulator, the operator is moving the master manipulator by applying some force, that force gets translated to some torques in all the actuator joints, and that torque information was sent to the slave side. So the rest of the structure of the controller is the same, but just we are adding the external force information on the slave side controller. So based on that, if we replace the control equation, these are the closed loop equation that we will end up with. And now we can show that the closed loop system will be stable using our using this Lebner function Vs. And based on the properties and the assumptions that we have considered, we can show that this Vs will be a negative semi-definite function, which will ensure that at least our system will converge to an equilibrium point. Then again, we are using an adaptive tuning law to tune the controller gains instead of choosing a constant controller gain, so that in case we do not have the information on the disturbance bounds, and also if we want to reduce the chattering and the input energy, then we can we can use this adaptively tuned controller gain. So the entire system stability can be improved using this Lebner function. So in order to do that, we have defined some lemmas, and this lemma actually simply comes from simple calculus. So based on this condition that we have achieved, we can show that this Lebner function that we previously defined, it can its time derivative can be given by equation 25, and this means that our system will be stable. That is basically, if we start at any initial condition, our V tot will be a decreasing function. However, we will have a offset in here that is given by half of eta k, and this is the expression for eta k, as you can see here, and it's governed by ki tilde, epsilon, and ki tilde. So basically, it is governed by the adaptively tuned controller gains. So we can, so it means the designer has the capacity to make the value of eta k as low as possible in order to improve the stability conditions of the system. So the entire controllers that were designed, that were implemented on, that were simulated on a bilateral system. So both the robot arms have, so in this work we are considering that both the robot arms has the same structure, and so it is the parameters of the robot arm are given here, and the parameters of the controllers are all of these. And what we are doing is we are applying a force that looks like this at the end effector of the robot arm. So we are using a 2 degrees of freedom robot manipulator. So at the end effector, or the hand portion of the robot arm, on the y-axis direction, we are applying this force, and on the x direction, we are not applying any force. So when we apply some force on the hand, the rest of the joints will start moving, or that force will get translated to the torques and for the rest of the joints. And the movement of the joints on both the sides, master and the slave side, our aim was to coordinate the movements between the two. So as you can see here is that we have this coordination. And the thing is that we have a communication delay. We have implemented the delay of up to 2.5 seconds. So this portion here, it is coming due to the delay. So these are the motions in the Cartesian coordinates or in the XY coordinates. And these are the torques that are developed in the joints of the robot arm. Here is the torque, that is translated torque from the external force to the manipulator joints. And these are the joint movements in their angular position, in terms of the angular position. These are the joint robot movements in terms of the angular positions. These are the tracking error. And then we have the adaptively tuned gain. As you can see here, that initially when our system states are very much away from the sliding surface, the gain is very high, and then as they reach the sliding surface, the gain also becomes low. So these are the sliding surfaces for master and the slave controllers for both the joints. And so now we have come to the conclusion. So what we found out was that with this controller, we were able to have a delay of up to 2.5 seconds. But beyond that, using the same controller parameters, the performance was bad. And we also did a stability analysis and a rigorous analysis to find out certain conditions so that we can pinpoint the parameters, or we can find out some ranges for the controller parameters. So as a future work, what we're going to do is do a further analysis to obtain a detailed information regarding the delay tolerance of the entire system. And this same method we will try to extend the same method to the multilateral tele manipulation system. So that is all. These are my references. Thank you.
Thank you, ma'am, for your nice presentation. Now session is open for discussion. So I request to participants, if you have any queries regarding this presentation, then you can ask. Yeah, Sandeep sir.
Yes, Dr. Navnita, I have a question regarding that your system model, and particularly the communication in between the master and the slave.
Yes, sir.
So is that the delay in the communication that hampers the stability of the slave?
Yes, sir, it actually does.
Okay.
Because we are actually so this is something that we did till now. Actually, we are now working on
Understand.
with the delay thing. Yes.
Understand. For example, you have done some simulation work. So
Yes.
have you seen increasing the delay does change the tracking?
Yes, actually, this is the maximum delay I was able to obtain with this particular controller and these particular parameters. So if it was maximum of up to 2.5 seconds is what I obtained. But if I increase the delay beyond this, this tracking is no longer possible. The system becomes unstable.
Okay, fine. So can you please go back to your system's block diagram once again? At that master and slave configuration. Yes, this one. So at that master manipulator, master controller, and you are communicating to slave controller, and okay, the master is also taking an input from the slave, right?
Yes.
Okay, fine. And all three delays are equal, right?
Here we are considering all the three delays are equal. Yes.
Okay. So there is a loop in between that slave and it's fed back to the master. So maybe that delay is creating problem in stability. Okay. So explore it more. Good work.
Oh yes.
Nice presentation.
Yes. Thank you, sir.
Sorry to interrupt you, ma'am. I have also one doubt. Ma'am, in your block diagram, you have seen that the information from the slave is also going to master.
Yes, sir.
Yeah. So the information that master controller is receiving according to that, he is giving some control action to the slave, or it is just taking the information only for his concern?
Yeah, actually what we are doing here is that this FH is actually giving the motion to the system.
Okay.
Here we are not giving any desired trajectory. We are simply holding, it's like holding the hand of a person and moving his hand. So this is what we are doing. So when we do that, if we do not, if we assume that the slave part is not present, then when we do that, this master arm will move, all the joints of the master arm will move at a certain trajectory. So what we want is that we want this trajectory to be followed by the slave as well.
Okay.
So at every point of time, we are trying to see whether that is happening. But the thing is that although in this paper we are assuming that there is no interaction with the environment on the slave side, but generally there is going to be some interaction torque or some interaction force. So that will be included on the slave side. So when that happens, we will again need to adjust, keep on adjusting the master side actuators so that the system does not become unstable. So which is why we need the feedback from the slave side onto the master side.
Okay, thank you, ma'am, for your wonderful presentation.
Yes,
So now we are moving to the last paper. That's paper ID is 74, and the title is Performance Comparison Between Higher Order Sliding Mode and Fixed Boundary Layer Sliding Mode Controller for a 10 degree of freedom bipedal robot. And the presenter is Koshela Cherfo. So I request to Koshela, please start.
Thank you for your introduction. So let me just set up my presentation. Can you see my screen?
Yeah, Kushela, your screen is not visible to us, and also your voice is some creating echo. Yeah, now it is visible. Yes.
Now it is visible?
Yes, yes. Please go ahead.
Okay. Thank you. So I'm Silchar. I'm a first-year master's student with Dr. Jason Gu at Dalhousie University. Today I'll present a performance comparison between higher order sliding mode control and fixed boundary layer sliding mode control for a 10 degrees of freedom bipedal robot. So we all know that sliding mode is a nonlinear control technique that is very known for its robustness. However, it has a chattering problem. So in this study, we will do a performance comparison between the known methods that solves the chattering problem. So we will look at the fixed boundary layer sliding mode control and the higher order sliding mode control. So we will look at the performance of position tracking, trajectory tracking, as well as the robustness of each of these controllers. So for the position tracking problem, our plant will be a 4 degrees of freedom robotic manipulator based on the Max Pincher robotic manipulator. And for the trajectory tracking problem, we will look at the a model based on the Tony Pi biped robot. So for our dynamics, we modeled our dynamics based on the Euler-Lagrange method, in which the Lagrangian equation is defined as the kinetic energy minus the potential energy. And with this, we can determine the torque equations for our system. And by rearranging that, we find that our dynamics is defined as theta double dot equals to f of theta dot theta plus g of theta tau plus delta, which is an added stochastic disturbance for our system. So now we'll talk about some of the math. So for the regular sliding mode control, as you may know, the sliding surface is defined as d over dt plus lambda times theta e, in which lambda is a positive constant and theta e is our state error. Then we define our control input tau as the equivalent plus the reaching control, which is g inverse theta times negative f of theta dot theta minus lambda theta dot minus k sine of s. And if we look at the stability of our system by defining a Lyapunov function 1/2 s transpose s and its derivative ss dot, which needs to meet the requirement of less or equal than 0, then we determine that our gain value k must be greater than the max value of the absolute value of s times sine of s. For the fixed boundary layer sliding mode control, all we do is replace that sine function by a saturation function, in which the saturation is -1 for all s values less than 1, s over alpha for all s values between -1 and 1, and 1 for all s values greater than 1. And here alpha is a positive constant. Next, we look at the super twisting second order sliding mode control. Here we define the sliding surface as d over dt plus lambda theta e. Our reaching control is lambda times square root of absolute value of s times sine of s plus omega, in which omega is just beta times the integral of sine of s dt. And by combining the equivalent with the reaching gain, we determine that our control input is g inverse theta times negative f theta dot theta minus lambda theta dot minus lambda square root of absolute value of s sine of s minus b times the integral of sine of s dt. And lastly, our third order sliding mode control. Here we define our sliding surface to be theta, s dot to be theta dot, s double dot to be theta double dot, which is also our system dynamics. And then s, the third derivative of s, to be just equal to f prime theta dot theta tau plus g prime of theta times tau prime. So here we define tau prime to be g prime of theta inverse times minus f prime theta dot theta tau minus k1s minus k2s dot minus k3s double dot minus k4 sine of s double dot. So here, all we have to do after is just integrate the tau prime to obtain our control input. So if we look at the performance comparison for the position tracking, we tuned all our controllers to have a rise time between 0.8 and 0.9 seconds with no overshoot. And for the regular sliding mode control, we see that we obtain a lot of chattering in our control input signal. And we also see some oscillations here in our phase trajectory. Here we see the system state response for the sliding mode control and the sliding surface over time. And again, we see some oscillations here, which is not desirable. For the results for the boundary layer sliding mode control, we can already see that the control inputs are much smoother. And we also get smoother sliding surfaces over time. For the second order sliding mode control, again, much smoother control inputs with smoother phase trajectory. And again, for the third order sliding mode control, very smooth control inputs and smooth phase trajectory. All right, so the results we obtained by adapting this to the position tracking problem, we determined that the boundary layer sliding mode control and second order sliding mode control perform well in low to medium range set points in terms of integral of absolute error times time, and integral of the error squared. We also saw that the second-order sliding mode control and third-order sliding mode control have high ISE index, indicating a slower but a smoother state response. And finally, we saw that the sliding mode control and third-order sliding mode control perform in high set point cases. So here we look at the robustness performance. So if you recall earlier in my presentation, I said that we added a delta term, which is a stochastic disturbance, in which we define it as A times the random function in MATLAB, which is just a function that returns a or a uniformly distributed number between 0 and 1. So if we set the amplitude of this function to be 0.5, we see here the IAE and ITAE as we vary the set points. So in this circumstance, all controllers perform well. However, if we increase it, if we increase the amplitude of the stochastic disturbance to 50, we see that the second-order sliding mode control takes much longer to converge to the settling point, whereas the third-order sliding mode control and the traditional sliding mode control perform fairly well. If we increase it even more, we see that the boundary layer sliding control does not converge at all and is unstable under this circumstance. The second-order sliding mode control takes much longer to converge to the settling point. And we see that the sliding mode control and third-order sliding mode control have by far the best performance as we increase the disturbance. So this can be seen in this figure, where we show the system state response as we have this value converge to the point, converge very fast to the settling point. So just to recap the results for the robustness comparison, at low disturbance amplitude, we see good performance by all controllers. However, as we increase it, we see that the second-order sliding mode control has noticeable oscillation and has long settling times. And when the disturbance amplitude is 100, then the boundary layer sliding mode control cannot converge at all. The second-order sliding mode control had very long settle time and is not ideal. And we see that the sliding mode control and the third-order sliding mode control perform best in high disturbance situations. So lastly, we'll look at the sliding mode control performance for the trajectory tracking problem. So in this case, we applied these controllers to a 10 degrees of freedom bipedal robot using the spring-loaded inverted pendulum walking gait for the biped. And here we show the ankle and hip joint state responses. So for this, the sliding mode control does converge to the desired trajectory as we want. Oh, and this is only for a single step movement. And we see here that the control input has a lot of chattering and is not ideal because it causes a lot of power losses and mechanical wear. So the performance of the boundary layer sliding mode control, we see that the control converges as desired. However, we have much smoother control inputs, which is much better for our mechanical hardware. And lastly, we applied the second order sliding mode control to the trajectory tracking problem. And again, we see fairly smooth control inputs, but with a little bit of chattering, which can be neglected. And so just to summarize the results, we see that the sliding mode control had good tracking performance, but has chattering leading to large power losses. The boundary layer sign mode control had good trajectory tracking, smooth control. And lastly, the second order sign mode control had excellent trajectory tracking performance in terms of integral absolute error and integral of absolute error multiplied by time. So just as a conclusion, in this study, we looked at the chattering problem. We observed that for most real-world applications, the boundary layer sign mode control and second order sign mode control are very good, as they perform very well in both position and trajectory tracking problems, having good IAE and ITAE. And compared to the third order sign mode control, it is very light in computation requirements. And lastly, we saw the third order sign mode control is far more robust, but is more computationally done. So these are my answers. If you have any questions, please.
Yeah, thank you, Kushila, for your nice presentation. So now the session is forum is open for discussion. So from the participant side, if you have any query regarding in this presentation, then you can ask.
Yes.
Yes, sir.
Yeah. What kind of disturbance you have taken here?
Sorry?
So, I have a request, Kaushila. You may switch on your video so that we can see. Actually, missed to ask previous presenters. Since we seen her in as organizing committee member. Still, I missed. So you can switch on your video. We can see.
Yes.
Yes, Manasa.
Yeah. Can you hear me? Can you hear me?
Kushila, yes, please respond. Kushila, are you there?
Yes.
Okay.
Yes, I can. Yes, I can hear you.
Yeah.
Can you hear me back?
Yes. What kind of disturbance you have considered?
Okay. So I considered mostly stochastic disturbance, so just added disturbance to the plot. So if we cut back here.
Yes. So you see, while sliding mode design, to find the gain condition, you should know the maximum bound of the disturbance. When you will do the stability analysis, you will find the relation between the gain condition with the maximum bound of the disturbance. So how, which property actually, I'm not, it is very much sure, it is not clear to me when you are dealing with stochastic disturbance. So what property you will consider about stochastic disturbance to design your gain condition of sliding mode controller?
So for the first order sliding mode control, I went through the stability analysis, and we defined that the gain must be greater than the max value of the absolute value of the disturbance. So
no, in case of stochastics, that is the confusion to me. That what do you mean by the?
I'm not sure if this is what you're asking. Right. So
because you know only the
status normally distributed, you will have
of disturbance.
Sorry, could you say that again?
Yeah, I'm telling that when you are dealing with this kind of disturbances, only the statistical properties are known. That mean, deviation, all these things are known. So then how you are correlating that design of controller gain with the properties of these 6 disturbances?
I'm not sure to understand your question.
Okay, fine, no problem. Can you go to the second order that
sorry.
yes, here actually you have missed W derivative, I think sign you have missed in this slide. If it is a super twisting, then
right,
one derivative sign I think you have missed here.
Omega dot.
Okay, yeah, omega dot, and then omega is equal to something, some mistake or okay, fine. From my side it is okay, and Sandeep sir can ask.
Okay. Okay, so I will ask. Typically, I had doubt regarding the parameter A. Parameter A you have considered for the robustness analysis through simulation, right? Parameter A, variation in parameter A.
Right, that is the amplitude of the disturbance.
Amplitude of the disturbance. Okay, this is the amplitude of the disturbance.
Right. So the random function in MATLAB, it returns a normally distributed value between 0 and 1. And so all we're doing with the A value is just amplifying that gain.
So it defines the maximum value of the disturbance as well, right? Because A into 1 is the maximum value. This A defines the maximum value of the disturbance as well, means maximum possible value, because A into 1 is the maximum possible value for the disturbance, right?
Right.
Okay. So okay, so that could be the disturbance bound. Okay. Then I have another query regarding that higher order sliding mode control. So is it that you have 10 degree of freedom system? So does it require more and more order of control? Means if we use more higher order, for example, second or third order, or even higher than that, so does it improve the performance of a 10 degree of freedom system? Means is there any relation between that degree of freedom and higher order control that you use in sliding mode control?
So we actually didn't implement the third order sliding mode control for the 10 degrees of freedom biped because the dynamics are so large for such a system that going through the derivatives was just not that easy, right?
Yes.
So
is it that if we use higher order controller or more higher order controller, even beyond that third order one, for example, fourth order, then does it keep better control for the for your system?
Well, as we saw, it depends on the case. For the if we compare it with the robotic manipulator, we saw that the third degree of freedom, or the third order sliding mode control, only performs well in higher orders or in high set points, right? So it depends. We would have to test that and see what the performance of that higher order sliding mode control would be. But yeah.
Okay. Thank you for the nice presentation. So any other question, Dr. Pal?
Thank you.
No sir. Thank you, Kushala, for your presentation. Now I request to Manas sir to wind up this session, and please sir, over to Manas sir.
Oh, the problem is saying that the chair should come to the session.
Okay. So we collaborate. in that act.
Yeah, definitely, sir. Sandeep sir, we are very much thankful to you that you have given time to spend with us, and also you have given your valuable suggestions to our participants. I think they will improve their literature as well as their work, what they are doing in future. And now I will request Sandeep sir to conclude the session with his valuable view about this session.
Okay, thank you, Manoj sir, and thank you all the participants. I can see that all the papers have been presented, and thank you your participation and nice presentation, and remain active or being active throughout the session. And thank you other listeners as well, though we did not receive any questions or queries from them. So still thank you for joining us. And thank you Dr. Manoj Kumar Bera, and thank you Dr. Bipin Chandra Pal for helping us in organizing the session, and for raising the nice questions. So we conclude here, and we request the participants to leave out, and the audience as well, and we'll have some discussion, and we may go for off record for that discussion.
Yes.
Manoj sir? Okay.
Yes.
Yes, sir. Yes.
So thank you all the participants. So you may leave. Yes.
Sir, thank you very much for
Thank you.
the entire session and for conducting the session. Since I am also a participant, I'll leave you to the discussion, and then I'll later end.
Yes. I expect. Thank you. So can you help us by switching off the recording for this?
Oh yes, sir. Sure. I'll
Okay. Thank you.
Okay, sir. It's stopped now.
Okay.
So, okay, I'll leave you. Okay.